What we're going to talk about today is optimization. I can't even get the highlighter to come up, but optimization. Now, that comes from the word optimal or optimum, which means the best. Now, when we talk about optimization, we're not talking necessarily about the best. What we are talking about is the biggest or the smallest. Now, if you hear somebody say, what is the optimum size of the group? That means what's the best size? What's the perfect size for that group to be? For us, it means biggest and smallest. You should have a set of notes on your desk, Daly. Now, Daly, I've counted you absent. Don't let me forget to take you off, okay? I'm going to give you an example. You have this great idea and you're taking it to Shark Tank, right? But it's for this new drink, and it's just, it's this power drink, right? And so you're trying to decide what kind of can do I want to put it in. I know I want the container to hold 32 ounces. And I know I would need it to look like a traditional can made out of aluminum. What is the optimum size? Meaning, what is the size of that can in terms of diameter and height, where I could hold that 32 ounces but use the least amount of aluminum possible? The less aluminum you use, the less it costs to build your cans, right? I say, I work for UPS or FedEx. And hypothetically, let's just say all of the boxes that I'm going to put in my truck are going to be the same dimensions. What are the smallest dimensions that I could use in order to get the most, how do I want to say that? If I know I need to have a box that holds 3 cubic feet of stuff, what is the best set of dimensions, length, width, and height for my box? Because if I can minimize the amount of cardboard that I use for my box, then my boxes won't cost as much, right? That's an idea of optimization. Now, Sparks has 5 steps to solving optimization problems. And if I stand here and write, and then you write, it's going to take us a long time. So what I'm going to do is I'm going to put this on the dot cam and let you copy these. I'm going to read through them, then you'll copy them, and then we'll talk about them. If I can get them to work. Dun, 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 dun. Mm-mm. No, it doesn't. I wish it did. Oh, hang on just a minute. Let me turn off my recording. Now that you have the 5 steps, we're going to go on and actually start solving some problems, and I'm glad you're paying attention. Now, essentially, what you've done so far, you've learned how to use a hammer, and you've learned how to use a saw, and you've learned how to use a screwdriver. Now you're going to start learning how to build a doghouse, okay? So we're going to start taking the tools that you have learned and actually do something with them. All right. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with the maximum volume, and what is that volume? All right. If you took Lashley for geometry, you know 3 of her favorite words were draw a picture. Mm-hmm. Yep. And that's going to be the 3 favorite words for optimization problems. If you can. Draw a picture. So what we're going to do is we're going to draw a picture of an open box that has a square base. Mm-hmm. Now, this says that there's a square base. How can we indicate using variables that the base is a square? Same variable. So what I'm going to do is I'm going to let these dimensions be x. Now notice it did not tell us that the box was cube. It told us that the box had a square base. So the height may be the same as the sides of the base, but we can't assume it, so we have to make it different. So we're just going to call the height y. Now, so we have a picture. What are we trying to maximize? So I want you to write maximize volume. Now I'm doing the steps that Spark says, I just may not be doing them in exactly the same order. Because he says determine the quantity to be maximized or minimized. That's his first thing. I start always by drawing pictures. So I've got what we want to maximize. And then is number 2 draw a picture? Yeah. Now what we want to do is we want to start writing an equation for whatever it is we want to maximize or minimize. We want to maximize volume. Length times width times height. So in this case, 2x? Yeah, x squared y. Now here's the deal. What v is equal to has 2 variables in it. So that's when we're going to go to that step that says you may need a secondary equation. What we have to do here is we have to get this x squared y down to just having one variable, because we do not want to differentiate implicitly because we are not given any derivatives. But we do know something else about this box other than volume. We know surface area, and we can actually write an equation for the surface area. How would we write an equation, or let's go back, an expression, so no equal sign yet, for the surface area of this box? And don't think, I don't remember the formula. There's not a formula. Just do it. There's no lid. What's the area of the base? X squared. What is the area of one face? X times y. And how many of those are there? So what is the surface area of this open box? That's it. X squared plus 4xy. No, but if it's at the bottom, it ain't going to hold anything. It could be on the side, I suppose, if you're making a cat hotel or something. Anytime that we're told an open box, we have to assume that it means the top. But we know what the surface area is. Our secondary equation, we will always be told something about it. So you think, okay, fine. Why is this secondary equation going to help me? Because if I can solve this for either x or y and substitute that into my volume equation, then I'll only have one variable in my volume equation, just x or y. Now I want you to look at that blue equation. Which of those variables do you think it would be easier to make it say, or to solve for, x or y? I agree. Let's solve that equation for y. I just did it all in one step, subtracted x squared and divided by 4x. Questions so far? Aha, I know what y is. It is indeed. So what I'm going to do is I'm going to take that and I'm going to substitute it right here. Now why can I do that? Well, crap, they came from the same box. So these relationships hold true for volume and surface area because they came from the same darn box. So volume equals x squared times y. Now, are you with me so far? If you can get to this piece, you got the hardest part done. Now, I'm going to write this as v of x now because x is my only variable. I'm going to have to take the derivative of this because remember, if I want to maximize something, how do I maximize? How do I find the maximum? How do I find extrema? The zeros of the derivative. And I'm looking for where the derivative changes from positive to negative. Good. So we're going to have to take the derivative of this thing. If I do it from right here, it is absolutely possible. But I'm going to do the product rule, and inside the product rule, I'm going to have to do the quotient rule. And I don't think I want to do that. I want to see if I can make this a little bit easier to take the derivative of. So I need you to understand, some of you might decide, well, shoot, if she says that's hard, that's the way I'm going to do it. Fine, go for it. You'll get the same answer as I do if you do your work right. What I'm going to do is I'm just going to multiply that x squared. I'm just going to multiply them together, okay? And if I do that, do you notice that that happens? Okay, well, that's a good thing. So what I've got is 108x minus x cubed over 4. You with me? Now, there are different ways I could handle this one as well. I could rewrite this as 1/4 of 108x minus x cubed. That's easy to take the derivative of. Yes? Could I do Heidi-ho? Yes, but the bottom's a constant. So since the bottom's a constant, the derivative of the bottom is going to be 0. So the answer is yes, I could do that. So I could write it like this and take the derivative, or, and that's easy, or I could split this into two different fractions. 108 divided by 4, can you do that in your head? So I could write this as 27x minus 1/4 x cubed. You don't agree with what? You told me 27. Okay. Why? Okay. I would contend to you that this or the 1/4 times, either one of those is going to be real easy to take the derivative of. Let's go take the derivative. V prime equals what? Keep going. Good. Equals 0. I want to know that. Now I'm going to tell you this. A problem like this, I would expect you to not need a calculator. I don't know if he says calculator or not on this one. I don't think he says. How would we solve this without a calculator? I could subtract 27 from both sides, or I could add 3/4 x squared. Right? Either one? Does it matter? No. So I'm going to have 27 equals 3/4 x squared. am I going to solve it? How? How? Okay. X squared equals 3 goes into 27 9 times. 9 times 4 is 36. Why do I throw out the negative 6? Good. I cannot have negative dimensions on a box. So I know that the negative's not even going to work. What was I trying to do to the volume? Maximize it. Ladies and gentlemen, you're going to argue with me on this, and you just can argue all you want, but I'm grading your papers. You are going to put that on a number line, and you are going to make darn sure that that's a maximum. Okay? So you're going to do a sign chart. Check the derivative. So we need to go right back here. If x is 1, is the derivative going to be positive or negative? Positive. Now I put 10. If x is 10, is that derivative going to be positive or negative? Negative. Is x equals 6 a maximum? You betcha. Now we got to go answer the question. Please make sure you answer the question. What dimensions will produce a box with maximum volume? Do we? Yes, because y is one of the dimensions. So if x is 6, what is y? We're going to write a sentence, so you don't need to worry about putting inches on the 6 right now. If x is 6, what's that, 108 minus 36 over 24? Is that right? Here? Sure. Sure. What's that, 72 divided by 24? That's 3, I think. Is that 3? So y equals 3. I'm going to go right here because I don't want to have to keep scrolling. What dimensions will produce a box with maximum volume, and what is the maximum volume? A box with dimensions, what by what by what? And you're going to put your inches, 6 by 6 by 3 will produce a max volume of 6 times 6 is 36, 36 times 3. 108. 108 what? Cubic inches. The fact that that volume and that surface area are the same is absolutely coincidental. Yeah, that is probably never going to happen again. You're going to be like, oh, this is awesome. No. Make sure you answer the question using the words in the question, okay? Next. We got 20 minutes before you guys leave, okay? You ready? Example 2. Oh, please be following your syllabus, right? A box is to be built from a rectangular piece of cardboard that's 25 centimeters wide and 40 centimeters long by cutting out a square from each corner and then bending the sides up. Can you visualize that? You have a flat piece of cardboard. You cut a square out of each corner. Did I say a square piece of cardboard? That's not what I meant if that's what I said. You just have a flat piece of cardboard and you cut a square out of each corner and you fold up those sides. Let's draw that. Okay, look right there. I know. Well, you know how now there are boxes. You can actually buy like chicken broth in a box, but it's like lined with something so it doesn't leak. Don't ask me. I don't know. I'm working. If you got a problem with the problem, call Sparks. Okay, that's all I got to say. So you'll send him a strongly worded letter. All right. Now, not necessarily. I might have great big squares on the. Who knows? Anyway, can you visualize now if we cut out those squares and we fold along the dotted lines? Now, this is a little weird because you're not accounting for a lid. So it's like we're building a square, or we're building a rectangular bowl. Yeah. Yes. We just yeah, again, send a strongly worded letter to Mr. Sparks and tell him to rewrite the problem. So now, so what we've got here, this length is 25 centimeters and this length is 40 centimeters. Okay, I think we're not going to get through this, is what I think. What are the dimensions of the little squares? We're just going to call them X by X. Now, I don't have all of the support that I do on the other one. I'm going to draw now I'm going to draw my box folded up. Oh, thank you, dear. Oh, Crystal Bridges is calling, you betcha. Now, here's my question. What are the dimensions of this box now that it's been folded up? What's that? 40 minus 2x. That's good. That's 40 minus 2x. Oh, stop. There you go. There you go. Now, what are we trying to maximize or minimize? We are trying to maximize volume in the form of an amount of soup. So we are trying to maximize the volume. Always, please write down what you're trying to maximize or minimize because you may forget. So that means I need a formula for volume. Well, okay then. What's the volume of that box? Yep, it's 40 minus 2x times 25 minus 2x times x. Do we need a secondary equation? No, why? Good. I only have one variable. So this really is just v of x, isn't it? Because x is my only variable. So I'm ready to do what? I'm ready to differentiate. I'm ready to take the derivative because this is really just v of x. Now the question is, do we want to take the derivative as is? And if so, we would have to do what rule? The product rule. Now listen, how many things are you multiplying together there? So you'd have to do the derivative of the first times the other two, plus the derivative of the second times the other two, plus the derivative of the third times the other two. That's a long process. What would you like to try? You want to multiply it all out? If I multiply those, that's going to be what, 40x minus 2x squared times 25 minus 2x. Now, if we stopped here, what would we do? Product rule. Do you want to stop here and do product rule, or do you want to multiply it out? Those of you who want to do the product rule, go do the product rule. Some of you want to multiply it out? Okay. Now don't scream 40 times 25. I can't do that in my head. Yes, you can. What's 25 times 4? So what's 25 times 40? 1,000. What's that? Minus 80x squared? Is that right? Oh, whoops. You know what I didn't do? Oh, no. I haven't taken a derivative yet, have I? So this is just v of x. Okay. Now what are we going to do with it? We've got the function, right? And you wanted to multiply it all out, so that's done. But I'm trying to maximize volume. So what do I do with the formula for volume? Now I'm going to take the derivative. Those of you who are doing the product rule, are you done already?
No.
I'm going to tell you this. Go to your calculator and find your zeros. Find them all. All right. X equals 5 or 16 and what? Now, I want you to look at those two numbers. We are for sure going to have to put, well, fiddle. Look on your calculator. Can you tell which one of those derivatives changes? Let me back up. Can you tell at x equal 5, does the derivative change from positive to negative? Or can you not tell because it's almost vertical? Okay, if it's almost vertical, shorten your x minimum, x maximum. Still looks very straight? So, Catherine looked on her calculator and saw that at x equals 5, the derivative changed from positive to negative, so that's your maximum. I want to talk about why you don't even need to pay attention to 16 2/3 though. You go back to 16 2/3. Is there any way that you can cut a square out of each corner of this thing that's 16 2/3 centimeters? Why? You don't have a box. You don't even have cardboard, right? What is the biggest, absolutely the biggest square, the dimensions that you could cut out of this thing? Just under 12 and a half, right? Because what's half of 25? 12 and a half. So if you cut out a square that's 12 and a half long on each side, then you don't have any box. So as long as it's less than 12 and a half. So just keep that in your head as you work through these problems. 16 2/3 doesn't even make any sense, so I'm just going to kick that one out. All right. So now we've got our x, and our x was 5, right? All right, so let's answer the question. Find the size of the corner square that will produce a container that will hold the most amount of soup. What's the size of the corner square? 5 inch by 5 inch, or centimeter, right? A corner square that is 5 centimeters by 5 centimeters will produce a container that will hold the most amount of soup. Why does that disturb you?
Because you just cut this box. That's not going to seal.
It's that lined, it's lined like the boxes of chicken broth. They're lined with some. Oh, stop. We are not even going there. There you go. They're lined later. They're lined later.
Problem would be undefined. We hold 0, no matter what we say.
Example 3. A rectangular page is to contain 24 inches of print. I want you to think about books. You can have books that are like what you call normal size books, you know, roughly 8.5 by 11. But then you have coffee table books that can be a lot bigger. But then you have those little books, you know, little bitty books. So that's what I was thinking, actually. I just didn't say it. Yeah. A rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used?
Thank you.
All right. What are we trying to do? Maximize or minimize? Read. There's a word in there that tells you. Least. Least. So, what are we trying to minimize? No. I'm trying to minimize the amount of paper. So if I'm trying to minimize the amount of paper, what geometric shape am I trying, or geometric thing am I trying to minimize? Area, yeah. So I'm trying to minimize the area of the paper. And I'll get it in a second. I'm trying to minimize the area of the whole page, and that's going to be important. Now what I'm going to do is I'm going to draw with assistance from the smartboard. That's not the one I want. That's pretty good. This is my print. The top and bottom margins are 1.5 inches. The left and right margins are 1 inch. And I know the area of the printed part is 24 square inches. what I want to do is I want to figure out what's the least amount of paper I can use for a page. Now, because we are flat out going to run out of time, I'm just going to take you through this. You have two options. You can let like this be X, or you could let this be X. Okay? Now, which one? It really doesn't matter. They will both work. My choice is I'm going to let this be X. Now, I'm pretty sure I don't have a square piece of paper, which means I'm going to let that be Y. Again, I could have let the print be X times Y. I could have done that. Let's write an equation. I'm trying to minimize the area of the whole page. Write an equation for what we're trying to minimize. Area equals X times Y. Do I need a secondary equation? I do. What can I base that secondary equation off of?
The area of the print.
Good. That's right. So I'm going to do this times this. So what are those dimensions? I think I heard Nathan saying them. X minus 2 times. And we know that equals 24. Now, we need to solve this equation for either X or for Y. It does not matter. I'm just going to solve it for Y just because I like Y. I'm going to solve it for Y. Now, you can do this a couple ways. You could multiply all that out and then solve for Y, or I could solve for Y straight from here. How could I solve for Y straight from here? Divide both sides by X minus 2. That's right. So if I divide both sides by X minus 2, and then add 3, then that's what Y is. Are you with me? We're going to substitute that right here. So my area is going to equal X times Y. Oops, sorry about that. Somebody got the hiccups. Now we can think of this as A of X because X is my only variable. And I want to minimize. So what do I need to do? Differentiate or take the derivative. Now, do you want to take it from here? In which case you would have to do what rules? Product and quotient. I would do something different. I'd distribute that X. That way I don't have to do the product rule. So let's just do another rewrite. So that'll be 24x over x minus 2 plus 3x. That one's not hard. It's all right. It's all right. All right. Now let's take the derivative. So a prime of x, derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared plus the derivative of 3x. Now, yeah, we're running through this one by hand. This one really does work out pretty nice. Look at that numerator. What's the numerator? 24x minus 48 minus 24x. So isn't that negative 48 over x minus 2 quantity squared? I cannot get rid of one of the x minus 2's because x minus 2 is multiplied by this 24 but not by this 24x. It has to be a common to every term. What do I need this to equal? 0. How do we solve that by hand? Well, as soon as I get something on the other side, I'll cross multiply. So it's going to give me what? 3 times x minus 2 quantity squared equals 48. Tell me if I lose you. X minus 2 quantity squared equals 16. I'm sorry, I added this term to both sides. Square root gives me x minus 2 equals plus or minus.
Wait, where did it become positive?
I took this right here and I added this fraction to both sides. Is that yes, go on, or yes, I got it?
I just did the opposite.
So you subtracted 3? That's fine. That's fine. You can do that. I just use negatives as little as possible. We'll still get the same answers, but not in yellow. X equals, what's that, 2 plus or minus 4? What's that going to give you? 6 or, what do you know you can throw out? I know I can throw out the negative 2. Now listen, again, I do expect you to put 6 on a number line and verify. Let's pick 1 and let's pick 10, but you pick whatever you want. That's what I'm picking. If x is 1, what's my derivative? Let's go right here. If x is 1, if x is 1, that's negative 1 squared, which is 1, right? Negative 48 divided by 1 plus 3, that's negative. If x is 10, 10 minus 2, 8 squared is 64. Is negative 48 divided by 64 bigger than 1 or smaller than 1? Smaller. When you add it to 3, you're going to get a positive or negative? You're going to get a positive. Is 6 a max or a min? 6 is a minimum. Did you want it to be a minimum?
Yes.
You dang right you did. So we got x equals 6. If x equals 6, what's y? Nine. Put it right here. Now let's write a sentence for our answer. What did the question ask us? What should the dimensions of the page be so the least amount of paper is used? The dimensions should be inches, 6 inches by 9 inches to use the least amount of paper. How you doing? You feel like you're starting to learn how to build a doghouse? Sorry?
Just worried.
Okay, we have two more. I think we can get through this one. What I want to do on the last one is just give you a clue, okay? So let's start with this one. A rectangle is bounded by the x and y axes and the graph of y equals 3 minus a half x. So this line right here is y equals 3 minus a half x. What length and width should the rectangle have so that its area is at a maximum? What am I trying to maximize? Area of that rectangle. And do not, so help me to goodness, do not look in there and say, oh, I think that's about 3.2 by 1.2. You do not do that. What's this length right here? And please don't tell me it's 3.2. That's x. Because this point right here is xy, right? So this is y. What's an equation for the area of that thing? That's it. Do we need a secondary equation?
Yes.
Yes. Where am I going to get a secondary equation? I've already got one. It's the equation of the line. Right. So area equals x times y. What do I need to do with that? Distribute the x and then take the derivative or differentiate. Yeah, that's fine. 3x minus 1/2 x squared. Take the derivative. Well, that's easy. What's x? And remember, because I'm grading your papers, you dang better make sure that you show on a number line that this thing, or on a sign chart, that that thing really is a whatever it is we want it to be. Well, our derivative sitting right here is 3 minus 1, positive or negative? 3 minus 5. So x equal 3 is a max. Is that what we were looking for? Ha ha. What length and width should the rectangle have so that its area is at a maximum? The rectangle's dimensions should be, we don't have any units, so don't worry about them. 3 by, what'd you say, Nathan? 3 halves, or you can put 1.5, it doesn't matter. To maximize area. You do not have to write the word units. Doing okay? No.
Let's just start it.
Well, I agree.
Let's pretend we're gonna finish.
I don't have a 3.5 anywhere, Sweet Pea.
Oh, so that's 3 halves.
That's 3 by 3 halves. So the 3 came from our x equal 3.
Because when we plug it into y, it's 3 minus 3 over 2, and that's just 1/2, and 3 minus 1.5 is 1/2.
Yeah, please ask. Don't worry about it. Determine the point on the line y equals 2x plus 3, which is this line right here, so that the distance between the line and the point 1, 2 is at a minimum. I want to minimize the distance between that point and that line. Perpendicular. Now, what am I trying? Listen, you know that has to be perpendicular. So let me give you a couple ideas. What are you trying to minimize? Distance, right? So you're right, minimize distance. Oh, but you have a formula for distance from geometry. Yeah, you have a formula for distance from geometry and you have a tune. So keep in mind, you're going to need ultimately to find that point right there. You're going to need to find that point so you can calculate the distance between them. It will be posted. You can read through Sparks' explanation. If you get stuck with anything, holler at me next week, okay?